Hello everyone and welcome to Engineering Statics. Today what we're going to go over is an introduction of vectors as far as they relate to statics, and I'll basically go through the theoretical explanation of how vectors work. Okay, so a vector. A vector is basically a couple of points in space with a direction. A vector is something that has magnitude, some length associated with it, and direction, some angle with respect to the axes. So if we think of these axes as y and x right here, then this is a two-dimensional vector that has an x component and a y component. Vectors in a 2D plane are basically triangles. You can break them down into triangles. So you've got the x distance and the y distance right here, and you can turn this into whatever you want. These can be some distance like 5 and 2 and so on and so forth, and then you can use Pythagoras' theorem or other trig identities in order to find characteristics of this vector, like its angle or its length or anything like that. Now, vectors in statics, we don't work in x and y. Axes are set up in x and y, but in order to denote the direction of a vector, you use I, j, and k for the direction of the vector. And now, how these work is they're basically a substitution for x, y, and z. So I is the same as a direction in the x direction, j is the same as the direction in y, and k is the same as the direction in z. So if you have a three-dimensional axis where you have x, y, and z, something like this, then this vector moving out into space somewhere would have an x component like this, a y component like this, and a z component like this. So if you move in the x direction, and then in the y direction, and then up in z. And this would be k, j, and I. And that is how the vector would be denoted in three-dimensional space. Okay. Now just a couple of basic vector math rules here as far as an introduction. When you're looking at this vector and you want to denote the length of this vector with respect to this axis, so where's the location of this vector and how long is it in actual three-dimensional space or in a two-dimensional space? If you look at this vector right here, I'll draw a new one, make it a little bigger here so it'll be easier. We'll have point B up here and point A down here, and we'll call this vector RAB. So the vector from A to B, we'll call it small r. It's got a component, an I component, and a j component. So this is y and x, which means this is going to be an I and a j. Now, how do you actually denote this vector? How do you find the length of this component and the length of this component in order to find the total length of the vector? Well, it's a triangle, but these points are measured in the x and y distance. This point is like, say, x1, y1. That's that point, and then this is x2, y2. I'm going to use variables right now. I'll do an example a little in another video. But in order to find this length, well, yes, you could use the line formula of x2, y2 and get the slope and so on and so forth. But since we're working in triangles, this will be a little bit easier to think of this as components. So how long is this? Well, it's going to be xb, x2, minus x1 in the I direction. So that's going to be basically this length right here. And then this vector right here will be y2 minus y1 j, because this is the distance in the j direction and this is the distance in the y direction. And as I said before, these are exactly the formulas you would use to find slope or distance of a line in a normal 2D graph. The thing is, when you get into 3 dimensions, that gets a little hairy, so you want to make sure you can break it down into I and j components. But any vector then, this total vector, RAB, will then AB will equal x2 minus x1 I plus y2 minus y1 j. So whenever you make up a vector in statics, you want to keep it in components of I, j, and k. If for some reason we had this was in 3 dimensions, you would just add on z2 minus z1k, and it would continue on like that. This is really important because as we get deeper into statics, you'll see how these can be added and manipulated and kind of turned around. So you can't use just standard high school geometry or trigonometry to solve these problems. So it's really important to understand these vectors. And really, all vectors are made up of a couple of points that are in some direction, and you do this real basic math to define them using these 3 basic directions. All right, I'm going to do an example in the next video of how to solve for forces, basically, in a vector form for a truss problem.